Hello, everyone. I am Nguyen, co-first author of this work. On behalf of my team, I am pleased to be here and giving this presentation of our work on robust distributed systems, FedDRL, deep reinforcement learning-based adaptive aggregation for non-IID data in Federated Learning. This work was funded by Vingroup Joint Stock Company and Vingroup Innovation Foundation. The presentation goes as follows. First, I introduce shortly about the Federated Learning paradigm and then our motivation. Second, I'll discuss briefly about the two famous benchmarks in Federated Learning research. And in the third part, I shall give full details about the design of our proposal. And then we move to experiment setup and results. Finally, some discussion and conclusion. To start with, let me introduce the traditional Federated Learning paradigm. In the last few years, the number of mobile and IoT devices, as well as their computing power, has been rapidly growing, which gives rise to concerns about the data privacy. Federated Learning came up as one of the main paradigms that allow parallel training without collecting private data from the client-side sources. In particular, a Federated Learning system consists of a cloud server, and a large number of clients or each devices. The server and the clients exchange a shared model weights during the training process. The training process goes as follows. Excuse me, I would turn off my camera so that it would be more convenient. First, the server chooses a subset of clients randomly and then send the global weights to those clients. Then the clients perform self-training the received model on their private data sets. After the training process, the weights are sent back to the server where the final step takes place, and the server aggregates the client models to produce the next global model for the next round, and the process continues. The final target is to produce a global model that can generalize, or we say the target is to generate a global model that achieves highest accuracy on the IID testing dataset. However, it is not very easy to generalize if that model was trained on heterogeneous datasets, which is often the case in both research and real-life scenarios. For this, many existing works have considered and addressed the problem of data heterogeneity, and there are quite a number of distributions being studied of recent years. However, when we collect the data for one of our classification tasks in medical fields, we find that the data is heavily clustered, as we can see in the figure on the right. The reason is people with same sickness often get this similar medical treatment. In this case, the same pills, but in different quantity. And we name this cluster skew. And furthermore, about our motivation, we would like to design an algorithm that adapts with various heterogeneities instead of one particular heterogeneity. And we find that reinforcement learning have the potentials that we need to adapt. Now, let's have a look on the two most well-known benchmarks, FedAverage and FedProx. And FedAverage is very genuine in idea, which is demonstrated by its impact factors. The impact factors are proportional to the data volume of the clients, which means clients have more data will contribute more to the global model. The rationale behind this idea is that a large volume of data might indicate diverse and informative knowledge. But as we explained earlier about the data distribution, then this is not the case. Then we have FedProx, who equalize the impact factors, but add a novel local training strategy to the locals, and which is computed by the Euclidean distance from the current model and the initial model, so that it can avoid overfitting situations. In this work, we would like to keep the naive training process like in FedAverage. However, we would modify the server aggregation scheme so that the impact factors are adaptive. Now, for the main part, I would like to introduce some basic concepts of a reinforcement learning paradigm. In the reinforcement learning paradigm, we have an agent and an environment. The two interact with each one another by a sequence of actions and reactions, which is modeled by states, actions, and rewards. At every round, the agent will observe the current states and then perform an action accordingly. After that, it's observe the changes in the environment and deduce a reward. And from the reward, the agent will update its policy accordingly so that it achieves its final targets. The final target of a reinforcement learning agent is to maximize the total return, which is defined as the discounted sum of the rewards. A deep reinforcement learning agent is different from a normal one only in its representations of policy, which is a deep neural network. Other than that, mostly the same. This is the overview of our proposal. As can be seen here, we use a single agent integrated in the server, and the agent helps the server to compute the impact factors. At any given round, the clients, after receiving the global model, will instantly use that model to compute the inference loss on its training data set, and we denote this as L subscript B, B for before training. After the training process, it again compute the inference loss on the training data set, and we denote this as L subscript A, A for after training. After the process, the clients send along with the weights, the losses, and its data volume to the server. The server then compute the impact factors and aggregates, and then send the next global weights for the next round, as we can see here. Of course, it will also store an experience for reinforcement learning updates, as indicated on the left. This is the overview of our proposal. Now, I would like to be more specific about the design of the main components. First, the state. We define the state as a vector of inference losses before and after training, and the data volume of each client. An action is a vector of means and variance of the impact factor, from which we use a softmax to normalize the impact factors so that they sum up to 1. For example, the impact factor of client K is a random variable generated by a Gaussian distribution with mean UK and variance sigma K. UK and sigma K is computed from the agent, right? And finally, and most importantly, the reward. The design of the reward is crucial since the reward is the guidance signal toward optimality. We design the reward as the average of total loss and its biggest loss gaps. The rationale behind this is that when we maximizes the sum of the reward, then we actually minimizes the inference loss of all clients. And why do we use the inference loss? Because the inference loss represents the fitness of the global model to the client's heterogeneity. Okay, so now we are going to move to the network architecture. And we design a relatively light networks since heavy networks would take a lot of time to train. inspired by the DDPG algorithm, we use the total of 4 networks, 2 main networks and 2 target networks, in which the policy networks output the actions, while the value networks estimate the goodness of an action in a particular state. However, as we can see here, the sizes are quite different, since the policy network only input the states, but the value networks also the state and the actions. Both of the networks have 3 dense layers and 2 activation layers in between, and the output of the policy network also have a 10 activation layers. For the training scheme, we use a parallel training process, and the first stage we train with multiple workers at the same time with the same initial policy to ensure that the experience buffer is enriched enough for the second stage, where we use this experience buffer to retrain the network once again. The updating rules are quite standard for policy-based methods in reinforcement learning. And here are the details implementation of the algorithm. This is a very clear and in the text, so we want to skip it in order to keep the time. Now, we set up the experiments. We conduct experiments on a single machine only and equipped with 4 GPUs for parallelism. The 3 main scenarios that we would like to test are described on the right, as you can see here. The first is the non-IID Pareto, which is denoted as PA for short. The other 2 is cluster skew, with the number of sample varies. As you can see, the first one with equal sample for each client and will be denoted as CE, E for equal. And the other is CN, N for non-equal, but still cluster skew. And other hyperparameters are demonstrated in the tables, and you can see it here. We train with 1,000 communication rounds, and for each round, we have 10 clients participating in the training process. Here we show the top 1 accuracy. Also, another benchmark we use in this comparison is called single set. Now, in this setting, we collect all the data client and the client data, and we train the model centralized, which gives the best possible accuracy or the upper bound accuracy. Overall, the results show that our proposal outperforms the 2 other benchmarks in all the cases, and the improvements are more significant when it comes to a large number of participants. As we can see here, in CIFAR 100 with 100 clients, then our improvements are quite significant, up to 10%. This result show that our weighted aggregation method using reinforcement learning can be more effectively engage the clients from the smaller group, leading to better accuracy. In the case of fashion amnist and amnist, we consider FedDRL is equivalent to the benchmarks, since the improvement are, but not very significant. Here we have the conversion rates of the algorithms, which are represented by the number of communication rounds each approach needs to achieve the accuracy as in this table. And overall, our proposal converges quite fast and quite high, much faster than others in the case of fashion amnist and amnist, and also in better accuracy also. And here we have the accuracy curve averaged in 10 rounds for better visualization. And in this case of 10 clients, and we can see that FedDRL dominates the other two benchmarks, especially in the CE and the CN scenarios. Again, for 100 clients, the observation is the same. For CN and CE settings, our proposal shows superiority, while in the PA settings, we show quite equivalent. Now, we also conduct experiment to test the robustness of the algorithm by increasing the non-IID effect, by increasing the number of participating clients, and increasing the non-IID levels. And overall, FedDRL shows robustness with respect to the number of participants, as we can see from the figures. And FedDRL can adapt to high level of non-IID here also. And we also conduct experiments to test the overhead computing latency of our proposal. And as we can see from the figure, the overhead latency is acceptable. In conclusion, we have our contributions as follows. We are the first to introduce and conduct a detailed study on a novel non-IID data type named cluster skew non-IID and focus on the inter-client correlation. Secondly, we are the first to apply deep reinforcement learning to adaptively aggregate the client's models. And we shows that our proposal is highly flexible in multiple heterogeneities and is superior to the state-of-the-art, up to 10% in accuracy. And this is the end of my presentation. Thank you for listening.